covers chapter 17, which covers a kind of a basic introduction to tests of significance. That's going to be the majority of the remaining chapters in this book. Will talk about different tests of significance. So let's get a quick overview of what we're covering this chapter. So we're going to talk about the reasoning behind significant tests, how to state hypotheses. This is like a key sticking point. P-value and statistical significance. We're going to look at tests for a population mean and significance from a table. So, what is statistical inference? So, confidence intervals are one of the two most common types of statistical inference. We covered those in chapter 16. That's when we use a confidence interval as our goal is to estimate a population parameter. The second type of inference, which is what this chapter is an introduction to, is tests of significance. And this has a different goal. This has the goal to assess the evidence provided by the data and make some claim concerning a population. We can claim that the mean doesn't equal what we found. We can test the means above or below. We could also test the standard deviation, right? A test of significance is a formal procedure for comparing observed data with a claim. And we also call this hypothesis testing. So you might hear me go back and forth. And what we want to test with that claim is the truth. We want to assess the truth. So significant tests use an elaborate vocabulary, but the basic idea is simple. An outcome that would rarely happen if a claim were true is good evidence that the claim is not true. So an outcome that would rarely happen if a claim were true is good evidence that the claim is not true. So, for example, artificial sweeteners in colas gradually lose their sweetness over time, and manufacturers test for sweetness on a scale of -10 to 10, which I didn't know, but it's kind of interesting. The negative scores corresponding to a gain in sweetness, and the positive to a loss in sweetness. So suppose we know that for any cola, the sweetness loss scores vary from taster to taster according to a normal distribution with a standard deviation of 1. We love to see a standard deviation of 1. And the mean mu for all tasters measures loss of sweetness and is different for different colas. So here we have a data set, right? So we've got the sweetness losses. So negative is a gain, positive is a loss, but for 10 trained sweetness tasters. So we take this all together and we can calculate the mean. So the average sweetness loss is given by the sample mean of 0.3. That means most scores are positive. That is, most tasters found a loss of sweetness. But the losses are small. In 2 tasters, the negative scores, maybe 3, thought the cola had gained sweetness. Are these good data that evidence that the cola lost sweetness in storage? Is this enough evidence? Well, what we can do is we can make a claim and ask whether the data give evidence against it. So we seek evidence that there is a sweetness loss. So the claim we test is that there is not a loss. So when we have a null hypothesis, that's what this is, our initial thing, it's always going to have an equal sign. So in this case, the mean loss would be 0. We say there's no sweetness lost. And if the claim that our mean equals 0 is true, then the sampling distribution of x bar, our sample mean, from the 10 tasters would be normal with mean 0, and our standard deviation would be equal to 1, which was our population standard deviation, with sigma equals 1, over the square root of our sample size, which was 10, which gives me 0.31, right? So that's going to be our standard deviation for this hypothesis test. So here I have my mu, right? Our sample mean, we're saying there's no sweetness lost. And we have our new standard deviation, which is 0.316. So the point right here, 0.316, that would be +1 standard deviation above the mean, right? So our sample mean that we found is almost one whole entire standard deviation away from the mean. Interesting, right? So this is like our calculations we did, and we can locate our x bar of 0.3 in this distribution and comment on whether or not it's surprising. Now, it's only almost one standard deviation away from the mean, right? One standard deviation holds 68% of the data, right? It's not 2 or 3, right? If I got something like a mean of 1.02, I'd say that was more surprising, right? So let's practice stating our hypotheses in the next video.